Greetings, my fellow chemistry nerds in this world. I wanted to bring you a wonderful video on oxidation numbers. Very important in this unit and foundational to everything we're doing this week and next week. What we're going to use them for is to determine how many electrons are being transferred over the course of a reaction, where are the electrons coming from, like which atom in a compound are they coming from, and where are they going to. Oxidation numbers are assigned according to a set of rules, and I'll cover that in just a minute. But last, every single species in a reaction, every atom, ion, molecule, and compound that in a reaction will have its own oxidation number. Could be the same, could be different. All right, let's go learn how we actually assign oxidation numbers, and then we'll learn later how we use oxidation numbers. So there is a hierarchy of rules, and you can find this obviously here or in the PowerPoint if you wanted something a little bit more formal. But these are rules that you want to learn and know and be able to apply. Very simple. All right, so this is a hierarchy. What does that even mean? A hierarchy means that we always begin with rule number 1 before we apply rule number 2. Once I've applied rule number 1, then I'll apply rule number 2. And I can only apply rule number 2 as long as it does not contradict rule number 1. I can apply rule number 4 as long as it doesn't contradict rule 3, 2, and rule 1. Whichever rule, if there's ever a conflict, let's say I've got to go assign oxidation numbers and I'm getting a conflict between 2 and 3. Well, because this is a hierarchy, then rule 2 would win. All right, so we always start with the rule 1 and then work our way down through a compound. Let's go through these together and then we're going to get some practice assigning these, okay? All right, so oxidation numbers must sum to the charge of the atom, ion, compound, or molecule. All right, so what does that even mean? Let's go look at the examples real quick. So in these examples, what do I mean? I mean that whatever number that I assign to, let's focus in for just a minute on this one iron right here, okay? What's the charge? This is obviously a charge of 0. Rule 1 says oxidation numbers must sum to the charge of the atom, ion, compound, or molecule. Then whatever number you assign to that iron, it better sum to the charge on the iron. Well, that would just simply be 0. I want to write my oxidation numbers in green on this activity. So that would just be 0. So that's the oxidation number of the iron. Notice that sulfur, there's only just sulfur in this compound. So whatever number, going back to the first most important rule, whatever number you assign to the sulfur, I have to multiply by 8, and I better get 0. Well, what number do you multiply by 8 and get 0? That's got to be just simply 0. So we can actually go ahead and answer that one right off the bat. So likewise, rule number 1 says that whatever I assign to the, let's say, the oxygen and the chloride here, whatever number I come up with for the oxygen and assign to the chlorine as well, they better sum to the charge on the OCl minus ion, the hypochlorite ion. And so it has to sum to the charge of -1. Again, last but not least, whatever number I assign to the potassium, I have to multiply it by 3, add it to the oxidation number I assign to phosphorus, and then last but not least, to add that to whatever number I assign to the oxygen times 4, add all of that together, and I better get the charge of potassium phosphate. The sum of the oxidation numbers better equal 0. All right, so understanding that, let's go to rule number 2. It says metals in groups 1A, that's your first column on the far left on the periodic table. Group 2A, okay, that's the second most left column. And aluminum have +1, +2, and +3 oxidation numbers respectively. So it's just saying everything in the first column has a +1 oxidation number. Everything in the second column has a +2 oxidation number, then aluminum would have a +3. Let's go look at the next compound, potassium phosphate. Note that we do have potassium, and potassium, if you look at your periodic table, is in group 1A. which means then, according to what this was saying, in groups 1A, they get a +1 oxidation number. So coming down here, I now know this guy right here has to be +1. I still don't know phosphorus or oxygen, so I can't figure out what those are yet, so we'll have to move on. Rule number 3, it just says if you see hydrogen or fluorine, they're going to be +1 or -1. So we can go through, and you'll notice I'm kind of working every example at the same time here. Hopefully that's not confusing for you. So notice if I see a hydrogen or a fluorine in a compound, it's going to be +1 or -1 as long as it does not conflict with rule 2 or rule number 1. Okay, so going through here, I can see, oh, there's hydrogen right there. And so I know that's going to be a +1 automatically. Rule number 2 says that sodium will be +1. So here's a great example of what I mean when I say a conflict. Notice that rule number 3 says hydrogen would be should be a +1. But notice that's only true as long as I don't conflict rule 1 or 2. And notice that we assign sodium first because it's +1. So then hydrogen can't be +1 as well because +1 + 1 is equal to 2. And if you notice, the most important rule of them all, the very first rule, it says that whatever I assign to the hydrogen, I have to add it to the sodium, and I have to get the charge on sodium hydride. And the charge on sodium hydride, of course, is 0. So what number do I add to 1 to get 0? It's -1. So sodium hydride is a great example of a compound that you need to make sure that you assign in the correct order. Notice in both of these examples we have +1 here and +1 here, so we can assign those easily enough. And because there's only one other element, we can go ahead and figure out what the oxidation number here is. Notice again, water's neutral, so I'm going to take +1. I can do some of the algebra off in my notes over here. So I can say, I'm going to take that 2 right there, and I'm going to say 2 times the oxidation number of hydrogen plus whatever the oxidation number of oxygen is, which I don't know what it is, so we'll just call it X. That has to equal the total charge of water, which is 0. So obviously 2 times 1 is 2, plus X is 0, and so obviously X, subtract 2 from both sides, you get X is -2. And so now we know that this guy right here is -2. This, by the way, is how we use rule 1. We can do this again. Get rid of some of this stuff here. Let's do the same thing, but this time for hydrogen peroxide, which is H2O2. So again, I know that I'm going to take this little 2 here, and we have to make sure we account for those. So here we go. So 2 times +1. So I've got to take that guy's oxidation numbers plus 2 times whatever oxygen is. That's got to equal the sum of the charge of H2O2, which is 0. And so obviously we have 2 plus 2x, which is 0. So 2x is equal to, subtract 2 from both sides, you get 2x is equal to -2. Divide both sides by 2, you get x is equal to -1. And so students, now we know that oxygen here is -1. Hopefully this is all making sense now. Again, very, very straightforward in how we apply it. I think the big thing is just watching that hierarchy. Oxygen has a -2 oxidation number. Again, that's only as long as we don't conflict rules 3, 2, or 1. So if oxygen has a -2, then we can pretty much answer almost everyone else. So notice that oxygen is -1, so we can come right here and go, okay. I'm sorry, oxygen is -2. Yeah, rule 4 says oxygen is -2, so that takes care of that guy, which means that we can find the chlorine now in this compound. So I know that this is -2, chlorine, whatever I assign to chlorine, I have to add it to -2, get -1 out. So hopefully you can do the algebra yourself and figure out that's got to be a +1. We can now come in here and assign oxygen here, -2, because of rule 4. So why don't we set this up to doing some algebra. Again, watch out for that 3 right there. So whatever carbon is, and there's only one of it, we're going to add it to 3 times -2, and all of that has to sum to the charge of carbonate, which is -2. So then x is obviously, x plus, oops, apparently I can't do algebra right now. Try that one more time. So x minus 6 has to equal minus 2. So hopefully you can see, add 6 to both sides, you get x is equal to plus 4. So carbon in the carbonate has to be plus 4. Again, if I'm going too fast, feel free to pause the video at any time. Because we know oxygen is minus 2 now, we can actually write that guy out. This is the biphosphate ion. And so now we can figure out phosphorus's oxidation number. And again, I'll do it underneath. I strongly just watch out for that 4. So I know I'm going to take our hydrogen's oxidation number, which is plus 1. I'm going to add it to whatever phosphorus's oxidation number would be. Add that to 4 times negative 2, the oxidation number for oxygen, and sum all of that together, right? It has to, again, equal the charge of the species. That's got to be equal to negative 2. So doing some just basic, good old-fashioned algebra, you're going to get 1 plus x minus 8 is equal to negative 2. And so x is equal to, 1 minus 8 is minus 7, then add that 7 to both sides, and you're going to get plus 5. And there it is. We now know that this phosphorus here has to be plus 5, and I'll just kind of squeeze that in there.